In this video, we're going to talk about the voltage divider circuit. So here's an example, and our goal is to calculate the current flowing through the circuit and determine the voltage across R2. So we have a series circuit because there's only one path for the current to flow. And the first thing we need to do is calculate the total resistance. So it's going to be 10 plus 20, which is 30 ohms. Next, we need to calculate the current flowing in the circuit. So that's going to be based on Ohm's law, V equals IR. So the current flowing in the circuit is going to be the voltage of the battery divided by the total resistance. So that's 12 volts divided by 30 ohms. And so the current flowing in the circuit is 0.4 amps. Now, to calculate the voltage across R2, we could use V equals IR. So V2 is going to be the current in the circuit times R2. So that's 0.4 amps multiplied by 20 ohms. And so V2 is 8 volts. So that's the voltage across R2. Now, there's another way in which you can calculate that same answer. Now, you can use a formula to calculate the voltage across R2. We'll call it the output voltage. So the output voltage is going to be the voltage of the battery, which I'll use VT for that, times R2 divided by the total resistance R1 plus R2. So the voltage of the battery in this example is 12 volts. And R2 is 20. And R1 plus R2, that's 10 plus 20, so that's 30. So it's going to be 2/3 of 12 volts. So 12 times 20 divided by 30 is 8 volts. So that's another way in which you can calculate the output voltage. Try this example problem. Design a voltage divider circuit with an output of 6 volts and a current of 60 milliamps using a 12-volt battery. So take a minute and try this problem. Well, let's begin by drawing the circuit. So the circuit is going to look the same. Now, this circuit consumes 60 milliamps. So we need to calculate the total resistance of the circuit. So we can use V equals IR. So the voltage of the battery is 12. The current is 60 milliamps, but if we divide that by 1,000, that's 0.06 amps. And so R is going to be 12 divided by 0.06. So the total resistance is 200 ohms. So what that means is that R1 plus R2 has to add up to 200. Now notice that the output voltage is 6 volts. It's basically half of the voltage of the battery. If you want to decrease the voltage, if you want to cut it in half, what you need to do is you need to make sure that these two resistors are equal in value. So what two numbers add up to 200 and are equal to each other? So this has to be 100 and this has to be 100. In that case, we can have a current of 60 milliamps and an output voltage of 6 volts. So if the input voltage was 20 volts, the output voltage will be 10. It's going to be half of whatever the input voltage will be. Now this problem is similar but a little different. So go ahead and design a voltage divider circuit with an output of 12 volts and a current of 50 milliamps using a 20-volt battery. So take a minute and try that problem. So here we have a 20-volt battery, and there's a current of 50 milliamps flowing in this circuit. So just like before, the first thing we need to do is calculate the total resistance. So let's use Ohm's law to do that. So the voltage is 20 volts. The current is 50 milliamps. If we divide that by 1,000, that's 0.05 amps. And so R is going to be 20 divided by 0.05. So the total resistance is 400 ohms. So we know that R1 plus R2 has to be equal to 400. Now the output voltage across R2 is 12 volts. So how can we calculate R1 and R2 individually? Now let's use this equation. The output voltage is equal to the input voltage multiplied by R2 divided by R1 plus R2. So the output voltage of this circuit is 12 volts. The input voltage is the voltage of the battery, and that's 20. We don't know the value of R2 as of yet. However, we do know that R1 plus R2 is 400, so we can replace this with 400. So this equation allows us to solve for R2. So now it's all algebra at this point. So what's the first thing we should do? The first thing I would like to do is multiply both sides by 400. Let me see if I can fit it in here. By doing this, I can get rid of the fraction. So on the left side, it's going to be 400 times 12, which is 4,800. And so that's equal to 20 times R2. Now to isolate R2, I need to divide both sides by 20. So R2 is going to be 4,800 divided by 20. And so R2 is 240 ohms. So now I can use this equation to calculate R1. So I'm going to replace R2 with 400. So it's R1 plus 240 is equal to 400. Now I need to subtract both sides by 240. So R1 is 400 minus 240, so that's 160. So this is 160 ohms, and if this is 240 ohms, then the voltage across R2 will be 12 volts, and the current will be 50 milliamps in a circuit. Number 4, calculate the output voltage across R2 in the circuit shown below. Now, because these two resistors are equal in value, the output voltage will be half of the input voltage. So we know it's going to be 10 volts. But now here's the important part. What will be the voltage across R2 if a device with an internal resistance of 1K ohms is connected across it? So without a device, the voltage is 10 volts. So keep that in mind. Now, it's important to understand that if you connect this with a device, so it has its internal resistance of 1,000 ohms, which is 1 kilo ohm. So I'm going to enclose this because it's some sort of device. You need to understand that when you connect a device across R2, the voltage across R2 will decrease. And the reason for that is some of the current that's flowing through R1 will go in this direction. And so less current will be flowing through R2 than before. And so if you decrease the current flowing through a resistor, the voltage across that resistor will decrease. Now, as this resistor increases in value, the voltage drop across R2 will be less significant. So if you decrease the resistor, then this voltage across R2 will drop to a much greater extent. So let's calculate the voltage across R2, which is the same as the voltage across the 1000 ohm resistor, when this is 1000 ohms, and let's say when it's 10 ohms. The first thing that we need to do is we need to find or calculate the equivalent resistance, since these two resistors are in parallel. And so you could use this formula. The equivalent resistance is going to be 1 over R1. So that's, 1 over R2. That's 1 over 100. And 1 over the internal resistance value. So that's 1 over 1,000. And then raise it to the minus 1. So the equivalent resistance is 90.9 ohms. So now we can calculate the output voltage using the same formula. It's going to be the input voltage, but instead of R2, we're going to use the equivalent resistance of that circuit. So it's going to be the equivalent resistance of those two resistors divided by the equivalent resistor plus R1. So you can treat the equivalent resistance as the new R2 value. So the input voltage is 20, the equivalent resistance is 90.9, and it's going to be divided by 90.9 plus 100. So it's 20 times 90.9 divided by 190.9. And so the voltage is now 9.52 volts. So notice that it's less than 10 volts. So you need to take that into consideration whenever you're connecting a device across a voltage divider circuit. Now let's see how much the voltage will decrease by if we decrease the internal resistance of this device to 10 ohms. So let's change this number and make that 10. So first let's calculate the equivalent resistance of R2 and the internal resistance. So it's going to be 1 over R2 plus 1 over R raised to the minus 1. So that's 1 over 100 plus 1 over 10 raised to the negative 1. And so the equivalent resistance is 9.09 ohms. So now, to calculate the output voltage rather, it's going to be the input voltage, which is 20 times the equivalent resistance of the two resistors on the bottom. That's 9.09 divided by the equivalent resistance plus R1. So it's 9.09 times 20 divided by 109.09. So notice that the voltage greatly decreases to 1.67. It's much less than 10. So if you want to keep the voltage as close as 10 as possible, you should only use a device where the internal resistance of the device is a lot greater than R1 and R2. If it's significantly greater, then the voltage won't change as much. So for example, let's do one more problem. So we see that if this resistance is 10 times the value of one of these, the voltage decreased by almost 5% of its original value. So what we're going to do, let's see what happens if the internal resistance is 100 times greater than the value of R1 or R2. So this time, I'm going to make it 10,000 ohms. Or 10 kilo ohms. So let's start by calculating the equivalent resistance. So it's going to be 1 over 100 plus 1 over 10,000 raised to the minus 1. 1 over 10,000 is a very, very small number. So the equivalent resistance will still be approximately 100. So the bigger this value is, the less significant 1 over that value will be. But let me just show you how it works. So 1 over 100 plus 1 over 10,000 raised to the negative 1. This is going to be 99.01, which is very close to 100. And so the higher the internal resistance of the device, the better, because the equivalent resistance won't be very far from R2, which is what we want. So that means the voltage across R2 will be very close to 10. So now let's calculate it. The output voltage is going to equal the input voltage of 20 times the equivalent resistance of 99.01 divided by that value plus 100. So 20 times 99.01 divided by 199.01 is 9.95 volts. So notice that the voltage decreased by only 0.5%, which is good enough. So if you want to design a voltage divider circuit and you don't want the voltage to change more than 1%, I recommend that you should design your circuit in such a way that the internal resistance is at least 100 times the value of R2. Because when you add a resistor in parallel to R2, the equivalent resistance will decrease. So make sure it's 100 times the value of this resistor. You don't really have to worry about R1 much, but R2 is what you need to compare the internal resistance to. Number 5. A device with an internal resistance of 5 kilo ohms requires a voltage of 3 volts. Using a 12-volt battery, design a voltage divider circuit that meets such requirements. And also calculate the current that the circuit draws from the battery and the amount consumed by the device. So let's start with this circuit again. So this is R1, R2, and then we're going to have the device across R2. So we know that this is 5 kilo ohms. And if we want the voltage to be approximately 3 volts, R2 is going to have to be 100 times less than this value. So 5,000 divided by 100, this means this has to be approximately 50 ohms. Now, if the voltage across R2 is approximately 3 volts, and the total voltage of the battery is 12 volts, then the voltage across R1 must be 9 volts, because they have to add up to 12. Now, this may not be the exact answer, but it's simply an approximation. So if the voltage across R1 is 3 times as great as the voltage across R2, then this resistance must be approximately 3 times more than R2, so it has to be 150. Now let's calculate the output voltage across the device. So first we need to calculate the equivalent resistance. So it's going to be 1 over R2 plus 1 over the internal resistance, which is 5,000, raised to the minus 1. And so that's going to be 49.505. Now to calculate the output voltage, it's going to be the input voltage, which is 12, times the equivalent resistance of 49.505, divided by the equivalent resistance, plus R1, which is 150. So that's 12 times 49.505 divided by 199.505. And so the output voltage is going to be 2.98 volts, which is approximately 3 volts. So that's a quick and simple way to design a circuit where the voltage across this device will be approximately 3. Now there is one significant issue with the circuit. How much current does the device consume? So the actual voltage across these 2 points we realize is 2.98 volts. So to calculate the current flowing through this resistor, we can use the equation V equals IR. So the resistance is 5,000 ohms. So 2.98 divided by 5,000, that's 5.96 times 10 to the negative 4. Now let's multiply that by 1,000 so that we can convert it to milliamps. So the current that flows in this branch is 0.596 milliamps. Now how much current flows through this resistor? It's going to be 2.98 divided by 50. And so you should get 0.0596 amps. If you multiply that by 1,000, that's equal to 59.6 milliamps. Now, if we add those two numbers, 59.6 plus 0.596, that's equal to 60.2 milliamps. So that's how much power is delivered by the battery. So as you can see, in this circuit, the device only consumes a fraction of the current compared to the amount that's delivered by the battery. In terms of percentages, 0.596 divided by 60.2 times 100. It's only consuming about 1% of the current that's being delivered from the battery. And so it's not very efficient. So how can we design a circuit where we have 3 volts across the device and that is highly efficient? Because 99% of the energy delivered by the battery is not going into the device. And that's a problem. Now, perhaps you know the answer already, but if you don't, the most simplest way to make this circuit more efficient is simply to get rid of R2, just to replace the device with R2. So let's draw a new circuit. So we're still going to have a voltage divider circuit. However, the device is going to be placed here. We're going to replace R2 with the device. Now the calculations will be a lot more simpler in this example. So the voltage across the device, which we'll still call it the output voltage, that's going to equal the input voltage times the internal resistance of the device divided by the sum of the internal resistance plus R1. So our goal is to get exactly 3 volts. So that's the output voltage. The voltage of the battery is 12, and the internal resistance, we know it's 5K. And then we could solve for R1 if we need to. But because the numbers are simple, we really don't need to use the equation. We know that 9 volts will be across R1 because 9 plus 3 has to add up to 12. And so, since the voltage drop across R1 is 3 times greater than R, we know that R1 has to be 3 times this value. So it's going to be 5 times 3, so R1 is going to be 15 kilo ohms. And so this is a simple circuit in which the voltage across the device will be exactly 3, and at the same time, the current flowing through the device will be 3 volts divided by 5,000, which is 0.6 milliamps. So notice that all of the current that is delivered by the battery flows into the resistor. So no energy is wasted. And so this is the ideal circuit if you want to create a voltage divider for a device. You want to replace R2 with the device itself.